All right, welcome back, everyone. Ready for another deep dive. Today, we're going to be looking at some pretty cool AI research
Yeah.
that really made me stop and think, you know?
Good.
It's all about, can AI actually understand and critique how it solves math problems?
Interesting.
Not just getting the right answer, but like the actual thought process. So the paper we're diving into is called ProcessBench, Identifying Process Errors in Mathematical Reasoning.
Okay.
It was published just this week, December 10th, 2024, by the Quinn team over at Alibaba Inc.
I see.
And they created this whole new benchmark test to see if AI can spot errors, like step by step, in how a math problem is solved.
Hmm.
And the really cool part is they didn't just use AI that's specifically made for math. They threw in some more general language models, too.
Interesting. And what were the results?
Well, that's where things get interesting. To help us unpack all of this, I've got an expert in AI and machine learning with us today. So maybe we start with, what problem were these researchers even trying to solve? Why is it so important to know if AI can spot these reasoning errors in math?
Well, you see, it all ties back to this concept of scalable oversight.
Scalable oversight.
Yeah. As AI gets more and more powerful, more complex, we need ways to make sure we can still, supervise it effectively.
Right.
Especially in fields like math, where the reasoning can get very intricate.
Makes sense. And they didn't exactly use easy math problems for this test, right?
Oh, not at all. They used competition and Olympiad-level problems.
Wow.
Pulling from datasets like GSM8K, MATH, Olympiad-bench, and OmniMath. Tough stuff, even for humans.
So how do you even start testing something like that with AI? What did they do?
So they mainly used two types of AI models: process reward models, or PRMs for short, and then critic models,
Dope.
PRMs. Those are specifically trained to check each step of a math solution.
Got it.
While the critic models, those are more general, they're just prompted to critique the solution overall.
Interesting. And get this, they used 12 different AI models to actually generate the math solutions in the first place.
Oh, wow. So they had a variety.
Yeah, so they had a ton of different styles to work with, making the test a lot more robust. They even had to reformat the solutions to standardize, like how the steps were broken down. They call it step granularity.
Ah, I see. So it's all consistent.
Yeah, to make sure the AI wasn't getting tripped up by just formatting differences.
That's important.
And these solutions weren't just checked by anyone. They brought in a team of PhD-level math experts to annotate them for errors.
Wow, serious business.
Yeah, and even they had trouble sometimes. The paper mentions in section 3.2 that they had to throw out 30% of the solutions
Really?
because the experts couldn't agree if a step was actually wrong or not.
So even for humans, it can be subjective.
Exactly. It just goes to show how complex this whole idea of a process error can be in higher-level math.
That makes sense.
And another interesting thing they found, figure 3 shows that most of the errors were concentrated in those early steps of a solution.
Early steps. Why do you think that is?
Well, maybe the AI is making some initial assumption or taking a shortcut, even if it eventually gets to the right answer.
That's plausible.
And it's not just a few cases either. Table 2 shows a pretty big percentage of solutions had process errors, even when the final answer was correct.
Especially on the harder problem sets, I bet.
Yep, exactly. Which really highlights the point that just checking the final answer isn't enough.
You have to look at the whole reasoning process.
So how did those different types of AI models actually perform? Figure 4 shows, as you might expect, they all struggled more as the problems got harder.
Makes sense.
But were some better than others? If we take a look at Table 3,
Okay, table 3, let's see.
it looks like the existing PRMs, those specialized models, they generally did worse compared to the top critic models.
Particularly on those tougher problem sets.
Right, so maybe the way they're currently trained is limiting them somehow.
It's possible. But didn't they make a new PRM, the Quen 2.5 Math 7B PRM 800K?
Yes, and that one was trained entirely on data that was already annotated by humans.
Interesting. And how did that do?
It actually performed significantly better.
So it seems like having that human touch in the training data can really make a difference.
Yeah, it's pretty remarkable. Now, what about the critic models? They held their own against those specialized PRMs.
Why do you think that is?
Well, maybe it's because they can reason more broadly. They're not just evaluating each step in isolation. They're looking at the whole problem and solution together.
Yeah, that could definitely give them an edge.
And unsurprisingly, the larger models generally performed better. More processing power, more data to learn from.
Right. But it's interesting to see the open source model QWQ32B preview doing so well.
Yeah, almost as good as the proprietary GPT-4o.
Impressive.
And it's not just about the numbers either. They show an example critique from QWQ32B preview in Figure 5. And it's not just some error code. It's actually explaining its reasoning step by step.
Oh, wow, that's really interesting.
So it seems like it's not just about whether AI can solve these problems, but understanding how it gets there and being able to spot errors along the way.
I agree, and there's a lot more detail in the appendices of the paper.
Oh yeah, there's some fascinating tidbits in there. Let's jump into those next.
Yeah, like Appendix A, that one's really interesting. It shows how they actually reformatted the solutions.
Oh yeah.
Figure 6 gives you a side-by-side comparison. You've got an original solution from Qwen27B Instruct, and then the reformatted version, it was for that problem about finding the focus of an ellipse.
Oh, I remember that one. The original solution was kind of all over the place.
Exactly. The steps were all jumbled.
But after they reformatted it, it was so much clearer, easier to follow.
It made each paragraph a complete logical step in the reasoning, you know.
Right. It makes sense. Got to make sure everything's consistent so they can actually compare the AI models fairly.
Precisely.
And then in Appendix B, they go into all the different models they use to generate the solutions in the first place.
Ah, yes. Table 4 has the whole overview, which model was used for which problem set.
Super helpful.
And there's a footnote where they mention they found a little code bug with a couple of the models.
Oh, really?
Yeah, it's just a small thing, but it's good they're being transparent about it.
Definitely. Transparency is so important in research.
Absolutely. It lets other people double-check everything, try to replicate the results.
Makes sense. Makes sense. Now, Appendix C, that's where they get into training that new PRM model.
The Qwen 2.5 Math 7B PRM 800K, the one that did so well.
Yeah, they took that existing Qwen 2.5 Math 7B Instruct model and fine-tuned it on that PRM 800K dataset, which was already human annotated.
So they were building on what they already had, making it even better.
Exactly, and they were very careful to make sure there was no overlap between the training and test data.
Right, got to keep those separate, otherwise the results wouldn't be reliable.
Okay, now Appendix D, this is where I got really interested. They actually show the prompt they use for the critic models.
Oh, the prompt, that's cool.
Figure 7 has the whole thing. They give the AI the math problem, the solution broken down into paragraphs, and then ask it to find the first paragraph with an error.
Like a little detective game for the AI.
Exactly, trying to see if it can catch those reasoning slip-ups.
Clever.
And then lastly, in Appendix E, they give a super detailed breakdown of all the evaluation results.
I see.
Tables 5, 7, and 9, those are the important ones. They break it down by problem set, even include results for using greedy decoding.
So even more granularity for people who want to really dig into the data.
Yeah, lots of information for researchers who want to compare models or dig into the specifics.
They really went all out with the transparency and detail in this paper.
I agree. They didn't just focus on the big picture. They gave all the little details too, which is awesome.
It's really well done. It'll be a great benchmark for future research in this area, I think.
This paper has given me so much to think about.
Me too.
It really highlights how complex it is to teach AI to, things like a mathematician beyond just getting the right answer.
For sure. There's so much more to it than that.
We've talked about how they tested the AI, but how do they even define these process errors in the first place? How do you categorize something like that?
Yeah, they actually talk about that in section 3.1. They call it the process error taxonomy.
Process error taxonomy, okay.
So they define a process error as like a step in the solution that either strays from a mathematically sound approach or creates a logical inconsistency,
So not just any mistake, it has to be about the reasoning itself.
Exactly. And they even have this table, Table 1, that lists all the specific types of process errors they were looking for with examples and everything.
Oh, wow, let me see that.
Yeah, check it out.
Okay, so you've got things like incorrect calculation that makes sense, logical fallacy, incorrect theorem application, even unclear explanation.
Right. So it's not just about getting the numbers wrong. It's about the whole thought process behind it.
It's like a framework for understanding where AI can trip up in its mathematical thinking.
Exactly. And that's crucial, especially as AI starts playing a bigger role in, making decisions in important areas.
It's not enough to just get the right answer. We need to know how it got there and make sure that reasoning is solid.
I completely agree. And this research gives us some really valuable tools to do that. The ProcessBench benchmark, this process error taxonomy, it's a big step forward.
Yeah, it really makes you think about the future of AI and how we can ensure it's not just solving problems, but solving them in a way that we can understand and trust.
Absolutely.
Well, this has been an incredible deep dive. Thank you so much for breaking it all down for us.
It's been my pleasure.
And for our listeners, if you want to explore this even further, definitely check out the full paper. You can find it by searching for ProcessBench, Identifying Process Errors in Mathematical Reasoning by the Quen team at Alibaba Inc. And until next time, keep those brains buzzing, and we'll catch you on the next deep dive.